Now we turn to acids, another group of compounds. There are multiple definitions of acids. One definition is that an acid is a molecular compound that releases hydrogen ions when dissolved in water. Here, when we're talking about nomenclature, we're going to learn to recognize acids because that acidic hydrogen that comes off when the acid is dissolved in water is generally written first in the formula. So when you look at the formula for an acid, the first letter is going to be H. That tells us, oh, this is an acid. Acids are a separate type of compound. They have another way of being named. So you can't use the other rules on acids. You have to use acid rules for acids. Okay, so HCl. Now this is where it gets a little bit tricky. HCl, how many elements in that? Two. Are they nonmetals? Yes. So this also fits into the category of a binary molecular compound, doesn't it? And so here's a distinction that we make in Chem 1A that we kind of gloss over in Chem 3A. If this is in the gas state, which would be its pure form, we would consider it a molecular compound. It's really only an acid if it's dissolved in water. So when dissolved in water, it forms hydrogen ions and chloride ions. And when we have that AQ in parentheses, that means aqueous, which means dissolved in water. So HCl is named as an acid if it's dissolved in water. It's named as a binary molecular compound if it is not. Isn't that fun? So some characteristics of acids, they have a sour taste. Any of you guys like Sour Patch Kids? Yeah, my kids love Sour Patch Kids. Personally, I'm like, why would you put something so nasty in your mouth? What gives them their sour taste? It's acid. Now, are all acids horribly dangerous for you? No. Why are lemons sour? They have acid in them. Strawberries have that sour bite to them too, right? Most citrus fruit does. It's acid. Acids taste sour. Another characteristic of acids are that they dissolve many metals. Not all, but many of them. And their formulas generally start with H. Here we have an illustration of how, what acid is that? HCl. Hydrochloric acid can react with zinc metal and dissolve it, literally eat it away. Okay, so in this group of acids, we divide them into two categories. Chemists really seem to get off on categories, don't they? It's dividing everything into categories. Actually, human beings in general do that. You just haven't probably looked at this many flowcharts in such a short period of time before. Anyway, so there's two kinds. There's binary acids. These have hydrogen and one other nonmetal. So these are the ones that also would fit into the category of binary molecular compounds if they weren't in water. And then we have oxyacids. And this prefix oxy is a big clue. There's oxygen. Oxygen is one of the elements in an oxyacid. So these are going to contain hydrogen and one of the oxyanions that we've already looked at. And there's a little bit different way of naming both groups of acids, so we have to be able to identify them. So the binary acids, here we've got hydrogen and one other element. Could be chlorine or sulfur, whatever. So we take, these acids use hydro as a prefix, and then following that, well, let's just look at this part. So hydro is the prefix. We take the base name of that nonmetal element, we change the ending of it to ic, and then we add the word acid at the end. So these are going to have two names also. Hydro something ic in a space, that's the first name. Acid is the second name. So let's look at these. So HF, hydrofluoric acid. This is a binary acid. There's no oxygen in it. So we use the prefix hydro. And then we take the name fluorine and we change that into fluoric. Remember, there's no flour in fluorine. It's completely gluten-free. Hydrofluoric acid. How about the next one? Hydrosulfuric acid.
Do you not say dihydro?
You don't. Oh, I can't write and think at the same time. There's some glitch going on. Hydrosulfuric acid. We don't need to specify the number of hydrogens, and that's a good question. The reason we don't is that when we put this, when this is dissolved in water, it dissociates into ions, hydrogen ions and sulfide ions. So there would be two of those. So even though an acid is not an ionic compound, when you put it in water, it becomes ionic, it ionizes. And because we have charges involved, then we don't need prefixes to specify the number. So to help you remember, when do we use numerical prefixes and Roman numerals and when do we not? We only use those extra descriptors when we have to. Okay, we're trying to get the shortest possible name that everybody's going to understand. Here, because we know that this forms the sulfide ion, that tells us that there's going to be two hydrogens. Fluorine makes what charge of an ion? -1, right? And so there's one hydrogen ion for one fluoride ion when it ionizes in water. Very good question. Any other questions? The oxyacids. So when we look at these oxyacids, the names are based on the names of the oxyanions. So basically you can cover up the hydrogen and look at what's left, figure out the name of that. And of course we're going to modify it a little bit. So you find the name of the oxyanion. If it ends in -ate, you're going to change -ate to -ic. If it ends in -ite, you'll change -ite to -us. Does anybody remember the silly sentence I put on the memorization quiz list? Rick ate him before he could bite us. Okay, this is where that comes in handy. Because there are lots of things in chemistry where you've got two pairs and you have to decide how they're associated. You get a 50-50% chance of getting it right or wrong. And so for me, I need to find something that will help me associate these seemingly random things. So that crazy sentence, Rick ate him, I can't write that small, ate him before he could bite us. This helps you to associate those. And again, spelling sometimes has to be. So here's ite and us. Those go together. And here's ate and ick. So ick and ate are paired. Ite and us are paired. And then, so we take, like if it was well, that's a bad example. If it was chlorate, we change ate to ick. It becomes chloric. And then we put the word acid on the end. All acids have the word acid in their name. That's just a really nice thing, I think. So let's name these guys. Yeah, so we look at this and we ignore the hydrogen. ClO3 is, oops, blah. Push the wrong part of the screen. Okay, so this is chlorate. Oh, I didn't want that color. Chlorate. So we'll change that ate to ick, and we get chloric acid.
So with the oxy, you drop the hydrogen.
With the oxyacids, we do not use the hydro prefix. Yeah. And it's hard to keep those straight. Sometimes students seem to cover their bases, but, well, we'll just put hydro in front of all of them. Well, it doesn't really help. I may know what you're talking about, but we have to use the correct terminology. So what about this guy? Acetic acid. So cover up the H, and what's left is acetate. So again, we change ate to ic, and this becomes acetic acid. There's not a ton of examples here in the lecture, but you're going to have a ton when we do those worksheets in lab this afternoon. When we write the formulas for the acids, from the name, the acid names are really easy to recognize because they have the word acid in them, right? Sulfuric acid, is that an acid? Oh, yeah, it says acid, right? So that's pretty easy. So we know that if the name ends in acid, the formula is going to start with H. And when we're writing the formula, we think of the acid as if it were an ionic compound, even though acids are molecular compounds. But they're so closely related to ionic compounds because when you put them in water, they ionize. So we write the formula as if it were ionic. The hydro prefix is only used for the binary acid. No prefixes for the oxyacid. So we can tell the difference from the name. So with the oxyacids, if we're going to use that same sentence, Rick ate him before he could bite us. But now if the ending is ic, we know that the polyatomic ion's name ended in ate. And so that way we can figure out what the formula of the oxyanion is. Based on its charge, we know how many hydrogens it would need. So let's do these. And of course, the first one doesn't quite fit the pattern because I don't like the way they defined binary acid. I actually prefer that we talk about oxyacids and not oxyacids because this guy, hydrocyanic acid, is named like a binary acid even though technically it's not binary. Well, how do we even think about this? Cyanic. Cyanide, okay? So that comes from cyanide. Cyanide is Cn minus. The charge on the ion tells us how many hydrogens, because the hydrogens have a +1 charge. So +1 minus 1, this must be HCN. So this is the one guy we'll run into. He's named as a binary molecular acid, or binary acid. Is he technically binary? No, there's 3 elements. The books all seem to just ignore that. It bugs me. It bugs some students. Other students are like, yeah, whatever. Okay, so that one, icky. Okay, this one, though, this is going to follow the pattern. Okay, so phosphoric acid, is this a binary acid or an oxyacid? It's an oxyacid. We can tell that because it doesn't have the hydro prefix. So what that means is we have to take this ic ending off and change it to what? 8. Now, this syllable with sulfur and with phosphorus, there's this syllable that kind of appears and disappears sort of randomly. So that or actually just kind of disappears when we go back to phosphate. And that's, So what's the formula for phosphate?
PO4 3 minus.
PO4 3 minus. So how many hydrogens does it need? 3. So the formula for phosphoric acid is H3PO4. How about hypochlorous acid? Oxyacid or binary? Oxyacid. Hypo, similar to hydro, but not the same. So this is an oxyacid. Us gets changed to what? Ite. So this is from hypochlorite. What's the formula for hypochlorite?
CO2 3 minus.
ClO minus. So getting that just off the top of your head might be tough. What's chlorate? ClO3 minus. Okay, so that's the 8. That's the one we memorize. Chlorite is one less oxygen. That's the ite. Hypo is below that. So we knock off one more oxygen and we get ClO minus. So then for the acid, we need one hydrogen, HClO. Any questions? This is one of the little environmental topics in your textbook. There are some pollutants, such as these compounds here. What would this be named? Nitrogen monoxide, nitrogen dioxide, sulfur dioxide, sulfur trioxide. Are those acids? No. But they can react with water and form acids, and that's what gives us acid rain. We get these pollutants in the air, they come in contact with the water in the clouds, and they can form acids. And this has unpleasant effects, not only on the environment, like here, the trees. Trees don't like it when sulfuric acid gets on them. No living thing does. Here's an example of some statues. Okay, these were much more detailed to begin with. In fact, I think those are the same. This one's more detailed. This one's probably gotten more rain on it. It just eats away at the stone that the statues are made out of.